Record. So we started recording and we can start again after the terrible deadline for submission of the first assignment. I've seen that, well, there have been a certain number of submissions. I hope that in the next days, someone else will submit the first assignment. You know, you all know that it is not necessary to do that if you are planning to do the exam after the second semester. So, but in any case, if you plan to do the exam before February, you must deliver the assignment before the exam session, even with some penalty in the mark if you wait a long time. We are next to define the second assignment that I promised you that it will be faster, it will be simpler. And today, if you have time, at least tomorrow, I will present the second assignment. So the idea is to work as soon as possible on it, so to have time for the last one. Good. So we can go on and with some theory, some theoretical concept. The theoretical concept are we already introduced the concept of files. So just have a deeper insight in files in Linux, Unix organization that is really similar to file organization and in other operating system, in particular in Windows, in the Windows family. So let me share the screen. I will take the only thing I can't see. Let me because it has been closed. Yes, I see. Should be this one, okay. Okay, in the last class we have shown this scheme. It has been already, it is in Aula Web. So you see it's a bit better than the one I did in real time using the pen. It's just to recall you the concept. This is a structure of the file system, Unix-like or Linux-like. Windows file system is a bit more complex, but the philosophy is very similar. This is important because we know that the concept of file descriptor is central to connect all kind of input, output, and inter-process communication. So I want that you know some more some details about it. This is the classical regular file system on disk, in which we have directories, and we already have seen that, so I go fast, and single files. The idea is that the file system is a collection of inode or inode, depends on what you want to pronounce it. Inode are small pieces, smaller than the classical cluster on disk, For example, by default is 256 bytes. The inode is important to know that is the interface between the kernel and the external communication channel. And so we will see that inode is fetched and kept in the kernel space and always resident when you open a file. Maybe may it a regular file on disk or a pipe. So an inode is a collection of pointers to single elements that can be directories themselves or pointers to data of regular files. Here is the summary of the structure of a classical inode, in which we have administrative information, mode owners. Mode means capabilities of writing, reading, or browsing a directory. The owners means also the owner and group owner and similar. Timestamps, in general, there are three main timestamps: the creation time, access time, and modification time. And they cannot be modified, so they are managed by the kernel. And so block count is a counter that to check the dimensions of data and the consistency, and pointers to blocks. Direct blocks are blocks that are pointers to blocks of data, like in this case, this file, for example. No, not this case. This file, this short file. The short file is directly pointed. A long file may have pieces of data in different parts of the disk, so there are different pointers. And if there are many data, a pointer to an inode which holds only additional pointers to other data. So they are called direct pointers to data blocks, single indirect, a double indirect, or triple indirect. So you see that in this case, short files can be addressed very quickly, and data can be retrieved very quickly because we have direct pointer to data. Longer or wider files require a double jump or triple jump. In the possibility of having a triple indirect allows us to have gigabytes of data. In this case, they can be retrieved in a slower way, so to privilege short files in general. That's the idea. Another concept is that pointers, there can be multiple pointers to the same data. In this case, you have a sort of synonyms. So, for example, in this case, this is pointed by two different names. They are called links. And in general, the idea is that you may have one link if the name of some kind, a directory name or a file name, is just pointed just by only one inode. But you may have multiple references to the same file or to the same directory from other directories in the disk. So that's the general philosophy. So in any case, you must have here inside, not here, but somewhere, what is called the reference count. So any file is known to be named or known by more than one father. Let me say one directory name. The same file or the same directory can be a component of several directories. So there is a counter that says, okay, you're referenced by only one, by two, by three, by four, and so on and so forth. So that's the idea in general. So to know a file, to access a file, when you create a file or when you read a file, when you open the file in general, and you know that the system call gives you back the file descriptor. What is the file descriptor? So in the successive slides, we have just discussing which is the internal form of managing a file descriptor. The first thing you have to do is to retrieve the file itself. The file may be a regular file, like this one, data file, or a directory name that in any case is a file, since they are all referenced by the same structure, the inode structure. So you have to retrieve that. So if you know the inode, you know the file, regular file or directory. So the inode is the name of the entity you want to access or you want to create if you are creating a new file. Starting from root, because the structure, you know, everybody knows that is completely hierarchical. And so when you open a file, you just jump to the root. So you always have, you must have permanently the root inode permanently in memory, in the kernel memory. So the concept of, I can write here, but it's referenced somewhere in some other place. Well, sorry, disappeared. Mounted file system. What is a mounted file system? To mount is the term for having the connection with the file system. Connection with the file system means that you have the root inode in memory. That's a permanent. When you start a system, you must have some file system mounted. So you're ready. You know that some inode, particularly the root of the file system, is already in memory. Just like the standard input, standard output, and standard error file descriptors, that you know that every program run by a shell have already opened the file descriptor, the three main basic file descriptors. File descriptors are not the same thing as inode, and I will explain, but this is, in a sense, this is similar. A mounted file system means a file system that can be accessed by your processes, and is a file system which has a root in the kernel. There are special system calls and commands, general commands, to mount or unmount a file system, and we don't use them, so they are not on our slides. But you know, just look at the man system and check man mount or man unmount, and you will see what, or you mount, no, or unmount, what it says. But in practice, they do this. They put the inode of the root in memory. So when you open a file, you go descend the root. So I can close this, discarding, and okay. screen sharing is. Go back. Now let's jump on the slides and to quickly to see what to do with the inode and how inode represent not only regular files or directory or not files on the file system, but also pipes. Let me see if I have the slides. Okay. Okay. System calls and data structures at runtime. So very quickly, there's a lot of slides that with concept that you already know in the other pack of slides, that like the system calls for opening, closing, seeking on files, and other system calls. Just so there are few things I want to show. These are the main. Well, first I can show the last slide. The last slide is simply this: the last snapshot of the kernel, and the processes. So before this pack of slides, we didn't discuss this part. And even this one. These are the new elements in the kernel. So you have now an idea of all the kernel components. There is only one kernel component that is missing. That is the in some way is separated component, because it has been designed probably 10 years after this structure. So it's kept a bit separated, and that the interface with the network here is not represented. Only peripherals are of the same machine. So we are missing the connection between file descriptor and the network, what we are using in the socket that will be the next topic today. But nevertheless, these are the new concepts. So we want to, the mount table is very simple. The mount table is what I have addressed now. You can see more the details in a slide here. The mount table is exactly the inodes of the roots of the file system that are mounted, so it can be accessed. In Unix, Linux, and even in Mac or OS, you can mount, dismount a file system simply connecting the root of the file system. In Windows, for tradition, the file systems are mounted in a different ways, because the Windows inherits the terminology of the archaeological MS-DOS of the years 80s, in which the names of the file system were A, B, C, D, and so on and so forth. And C was the main file system with the operating system itself. That's the reason why when you open Windows, we start from C. A and B were floppy disks on the original personal computer by IBM. And now usually they're not in use anymore. But concept is in a sense similar. So the mount table is just the roots of the roots. Okay, this is the slash, it's a root. So it's simple. We must know what are the file descriptors, file table, and inode table. Buffer pool is the caching of the disk that is always supported by the kernel itself. So we go back now. We go back to to this slide. Okay, this is the no, just previous slide. Okay, here we are. This is part of the user area. So together with the, you know that in the user area, there are open file descriptors, and that's part of the, so it's process. This is the process itself. In the user area, there are file descriptors, 0, 1, 2, standard in, standard out, standard error, and other file descriptors. What is a file descriptor in the user area? There are pointers to the file table resident. These are the two tables that we have seen in the kernel space, and always resident. The simplest to understand is the inode table. Here there is the inode, the in-core inode table, in which all inodes involved by the process running are permanently in memory, directly in memory. To get these inodes, you must prior going to the mount table to check which is the root for this inode. In the inode table, this arrow means that this is a pointer to the disk. Directly, the pointer to the position of the inode in the disk. In the first part of the disk, or the file system of the disk, in the first blocks, there is a directory of all inodes. You know where inode is, and so you check, you find the inode and you load it in the table. For each inode, there is also the reference count. What is the reference count? Well, inodes are numbered from 0 to the last number, possible number in the disk, depending on the space on disk. The reference count says how many files use the same inode. That because you know that you may have, for example, in this case, this is referenced as file descriptor 0 here, but also may be referenced as the file descriptor n in another process. If they are referencing the same file, means the same inode, the reference count is 2. A reference count is important because why? In particular, is important because when you close a file or you delete a file, that is called unlink. Not. It's important that is the name of the system call is unlink, not remove. You simply decrease the reference count. When the reference count goes to 1, the next one who erases or closes the file put to 0, and the inode is put away from the inode table because it's not interested. And if you want to delete the file, you unlink and you are the last one who unlinks the file. So you ask the file system manager to release the inode, and and mark the inode as free inode that can be used to generate a new file. There are other information, for example, the modified flag that says, had it been modified since the last time it has been accessed, and so on. It might be useful for some other, in some cases. So that's the inode table, and this one table, because can be referenced by multiple pointers. This is a logical, we can think of the inode table as a hardware table, since they point exactly to a specific hardware address on the disk. The file table is logical in the sense that you have files that can be read, write, or written. And in that case, you have multiple entries, in any case with a reference count, and you have the mode, why you are using. For example, in this case, you can use the same inode for reading and writing. And this last byte accessed is the position. You know that the model is a sequential, a sort of electronic tape for recording and reading. And so, stream in C++, for example, in that case, you move the window or the head for reading or writing of one position just after you have read and write. So last byte accessed is just the index for reading and writing, the one that you can move when you use the seek system call. So you move forward or backward this pointer to the file for the next I/O operation. So these are the tables that are used when you have a file. And here is, I think there's no need to read and comment each line. There is a description step by step of what happens when you, for example, you open a file through the path name, looks for its inode, and the ilist on this. The ilist is a list of the inodes. Okay, it can be to return an error code. If the file exists, copies its inode into inode table and completes with the other information that are necessary. For example, the capabilities for writing, reading, the ownerships, and so on. Then going back just for one time, you create an entry in the file table, and you assess in the file table opening mode, reference count, and offset, for example, the beginning of the file. And then going back, create an entry in the file descriptor table of the process using the first, what is the first free entry? Is the file descriptor. The file descriptor. What is the file descriptor? File descriptor, when opening a file on disk, is the result of this three-step activity. Fetch the inode on disk, build an entry or two entries in the file table, if you read and write the same file, then going back, give a number that is the lowest, the smallest number, the first free entry. This is important because if you remember, using the duplication of file description, you always give the smallest integer number available, and so on. And this is how, what happens when you do this. And it's simple to do what happens if you, well, example, when you close, go backward and release the inode. Here is an example. So you use, I want that you understand exactly the machinery, how it works. There will be no oral exam, so I will never ask you write on the whiteboard or on the blackboard exactly which is the structure, but I want you to know the terminology and the system. Maybe I will ask you in the written exam something related to that. And another principle is that when you read going through the what is called the cache. The cache is not something external. It's part of the kernel. Cache is automatically aligned with the disk, but you always go inside the cache and read from the cache. And the opposite you do, you know where the cache is, so I don't have to comment this. And when you write, the same happens. You write on the cache, and sometimes the cache is aligned. Remember that in Unix, Linux, as well as OS, Mac OS, operating system, the cache is part of the kernel. So if you dismount physically a file system, because you unplug the file system or you unplug the memory stick, you surely you raise errors in the file systems, because this operations of keeping the cache aligned with the disk happens sometimes, not always, rarely, as rare as possible. Much part of the memory is used by as a cache for the disk. So you cannot. So it's a sort of, and it's important in all embedded system, in robotics or hardware managed directly by programs. When you have an automation system, keeping the cache aligned is very important. You know the flush, and some of you has found that it was necessary to use the flush system call, because otherwise some unforeseeable errors may arise. Flush is exactly an operation that a system call just to write immediately on disk what is simply written in the buffer cache, and the opposite also in reading. So flush is part of the operating system, is not an additional feature for dismounting an external memory. LSEEK, for example, is the family of the seek, and simply changes the last byte accessed in the file and so on. Here is a series of other names, and so that's the explanation of the file table, inode table, and file descriptor table, and how they are linked. We have seen in the buffer pools, and then last there. Process table, we already know what is a process table. Just a few remarks on, well, redirection of input and output is simply managing the names. There are examples here I skip. Please have a look to those slides that are clear, but just to understand the steps in which the basic system calls are implemented. Pipeline. A pipe is exactly, you know what it is. Oh, produttore consumatore is in Italian. I forgot to translate, but I think there's no problems. In any case, a pipe is just, okay, no differences. The only The only difference is that read and write offsets are here, not in the file table, because they are shared. But it's a minor difference. Both processes share those. So, but in any case, they're absolutely the same as regular files. And you know that named pipes are regular files, even kept in memory, so they guarantee to be managed directly by the memory and not by an external device, so they are faster. So there's no difference. File descriptors are always use this table, this triple. And there is an inode also for pipes. A pipe, unnamed pipe as a standard inode name that does not correspond to an physical inode on disk, but the method is the same. We are not we are not showing here how a file descriptor can be connected to the network. I think I will give you, well, I will skip this. We have time, some additional information. I will give you some information. But the fact is, in POSIX, they decided, and I think it's a very good idea, to use, in any case, the meaning, the semantics of the file descriptors, even for a network connection. With the bit of difference that cannot be completely reduced to the concept of file, because you know that there are two file descriptors for the same socket. But well, in the next slides I will recall you, because we need file sockets now to go on to do the next exercise and to do next assignment. So this is the story. Other data structures. Here is the concept of mount table. Mount and U-mount, non unmount. U-mount, please select the man mount and U-mount, and you know, but the effort is just to connect the inode, the root inode, to the put in the kernel. Concept of major and minor numbers of the device. We don't explain that. Major and minor number are maybe in the real-time course of some concept of that. But in any case, when you connect a device, because when you mount a file system on disk, you give the inode, of course, of the root, but you also have to tell the kernel which is the device driver of that disk, because a disk may have different device drivers. Drivers are part of the kernel, and what are called minor and major numbers refer to the device driver. They are integer numbers, as anything is in Unix, and different drivers inside the kernel have two numbers, a couple of numbers. The first one, major number, is the category, so the categorizes, or in a sort of hierarchy, very simple, two levels, or all disks, all sequential disks, or block devices, or keyboards, and so on. Okay, the major number, and the minor number is the specific driver inside. So when you mount, as a matter of fact, not only you load the inode of the root, but before doing that, you must tell the operating system which kind of component, of driver component, to use. So the first thing is when you mount, it does two things. connects the driver and uploads the inode. And not only the inode, but also the super block that is a block at the beginning of the disk, which contains information regarding the whole file system dimensions and other characteristics. So that's the concept of super block, and point to the root of the file system. And okay, directory in which is mounted. So I will hide this. It's a simple concept, but now is probably is misleading. So you can mount a file system not on top of the aside all other file systems mounted like Windows. That you know, when you mount a new file system, you have C, D, E, F, G, so they're all siblings. In that case, you can mount a file system aside another file system or inside another file system, which is something that is useful but not interesting to us now. And that's the back of the slides. Finished back. We are finished. You know everything about the well, you know, just a glance to the components of the file descriptor that is central to all communications inside the kernel. Okay, I stop share this. And so all study material for the file system is my drawing that you have seen before, and the speckle slides in which there are 5 or 6 slides that can be interesting, and I asking you to remember the name and all the components just to know the concept. So I can go on if you allow me to go on, and I shift to sockets. So because I want to do just after talking about sockets to retrieve some exercise I proposed you to work on, in particular those of designing a system. I will retrieve an old exercise. I will try to show an example how to solve that, and go directly to the assignment for the next assignment, going through a new exercise I will propose in groups just to discuss all together. Or novelty. As soon as I have described which is the next assignment, I will divide you in group probably tomorrow. Well, we'll see. And you will start discussing together that assignment. Not a general problem, but just directly the assignment. Okay, so sockets now. Well, just 1 minute. I have to drink some water, so please let me stop for a while, just 1 minute. We rest for changing the topic. Pause recording. I did not stop recording. So, okay, the recording includes also my absence. Going back to the sockets, we have already seen many things about sockets. So, okay, this was a slides on sockets. Can you hear the shared screen? Can you see the shared screen?
Yes,
Yes,
Professor.
can hear you and see the screen.
You hear it? Okay. Well, sockets are well. Let me see from the file descriptor side. You know that they are a way of exchanging information dynamically between processes on different machines, even on the same machine, but typically on different machines in the network. In any network of several networks, we refer only to internet because it's the most common way of making them communication. So they use the concept of host address, IP address, and port number. They are in two different levels of the internet ISO OSI model, but no, it's not important for us. I've explained a series of well, this is the typical concept of port. Let me recall you the concept. Port numbers are there are many ports. The lower ports are fixed, are registered. Lowest port cannot be changed because they refer to historically decided services that cannot be defined by you, by us in general. They can, but you must be administrator. And include, you see the dynamic name server, the mail delivery, file transfer, terminal connection, finger. Nobody uses finger anymore, but in any case, it's an old services. Managing of devices on the network and so on. The secure shell and the HTTP. A lot of protocols. There are standard protocols you cannot define again, but there's a lot of port numbers that you can decide freely, and the system, the processes running in the internet, when they connect, sometimes they use connection, instant connection, and use by themselves automatically some connections of this kind. They're called ephemerals. These are the concepts we have seen already. I want to just to go back on this slide. This is the typical structure. Let me. Okay. The most common structure, the most common architecture, let me say, of using sockets. The strange thing is that in general we have two different file descriptors. They are considered file descriptors, and here there are two different file descriptors. And you can use both, and it is important to understand why they are different and how to use them. This is called a passive socket in the sense that the server waits for a connection. Accept is blocking, but it not correspond to read that is blocked. Oh, okay. Another concept is that receive and send are correspond to read and write. Not only correspond, but instead of using receive and send, you can use read and write, the standard read and write with the file descriptor. And in the example I have uploaded in our web, read and write are used instead. And the same from the client side. Read is blocking, write is blocking, exactly like any read and write as IPC. There is some trick inside. That's the reason why receive and send are more bit more complex than read and write, because the idea of blocking is some semantics that we don't we are not interested in. But for example, when you write, but on the other side the connection is lost, what happens? Which kind of waiting, so, or blocking? So it's complex. So we don't think of this kind of problems. We think the connection is steady until you finish the session of communication. So in that case, read and write are absolutely indifferent. Receive and send can also manage strange situation that in normal IPC does not happen or raise errors. So going back, so reading is blocking like any read, but accept by self, it's blocking, but it does not transfer information. Accept just puts the server in a sleeping state until a request of connection is received. So accept is a sort of switch, Boolean switch. Accept is something that says, okay, a client has awakened me, so I raise and start again and can receive. But at the same time, accept gives you back a file descriptor. The file descriptor for that connection. So you read and write or send receive using that file descriptor. This is another file descriptor that defines the socket. So the socket is sort of super file descriptors, because inside the same connection, this is a connection. You may have different accepting states, you will see. Not in this case. So in this case, it seems useless to have socket by different from accept. Just define a socket, you bind, and you will see you are ready to accept, and then you wait. That's the normal structure. In this case, it's serial structure in the sense that you can loop here and send, receive what you want serially, or read, then receive, then write, and so on. And the same does the client, which has a series of steps that is simpler, just a socket, and connect is what starts the session. So unblocks the server. So just the socket that is exactly the same like in this case. Well, this is a general structure. Let's have a look to the code and to learn a new but very, very important concept that is not in these slides. Maybe I will put more, to avoid confusion, I will leave this part in the additional document. Stop share, and let me find the I have to find it, but no, not this one. Hope this is this one. No, this is the client. So hope that since there are 3 files, I hope that the third attempt I will. No. Sorry, let me see where it is. Server 2 line is no. Let me try this. Maybe we succeeded in that. So this is the example you have in Aula Web, an example that you can just copy, paste, and compile and try. So they're example that can run. They use a simplified version of parameters, and all lines of this code is commented very in details in the included document that you have published. So please read line by line and understand what's the meaning of everything. So the first thing you do is this. You define a socket, and in this case you simply say that is a internet socket and use the TCP socket, so the connection that is safe connection and safe and reliable, in which all packets of your communication are acknowledged and retransmitted in case of errors and so on. So you are sure that all communication will not fail. So that's the first step. And this is the first file descriptor. Okay. Then, okay, error management and so on. Then you bind the socket. It's a different, well, in some library in object programming, for example, the two system call are collapsed into one, because here, in more than the previous case, you just specify the address. That's the main information. So you say, okay, that's my address of. Here I said that this is a socket, a TCP socket, and here is my address. They're different system calls because you may change after having defined the socket. You may change the others, for example. In any case, 2 steps. Yes, please. No questions. Okay. So going on. So the second step is bind. Then you listen. Not many information here, because if you look here in that case, you always are referring to the same file descriptor. Also here, the socket file descriptor, socket file descriptor, socket file descriptor, and you simply listen. So you switch on the machine. So now you're waiting for connections. Listen. The number 5 means how many are in the queue, if there are many attempts at connecting, and so on. Doesn't matter. And third step, you see here that you have another file descriptor. A new file descriptor. The file descriptor now is the result of accepting a connection. It seems redundant because you already have a file descriptor, but now for reading or writing, you have to refer to this file descriptor, not to the socket file descriptor. It seems redundant and in some way useless. Well, you don't need that. But why 2 different file descriptors? You see, in that case, you read, you write, and the demo program is over. It's finished. Just one communication with the client. We can have a look at the client, and you will see that the client connects and writes and reads the message back. But what I wanted to point out that the protocol, let me say, in programming for coding is just to follow this scheme. Define a socket, bind the socket with your address, put the server in listen state, and that accept. Unblock when you accept from this file descriptor, in that case, but you have a new file descriptor. And from now on, you will, yes?
Professor, I have a question.
Yeah.
So in this particular program, would we have 2 file descriptors, simultaneously working, like the first one and the second one?
I will show you in the next example why there are 2. So there are 2 file descriptors, but the first one is used to call the accept. So when you say, I am accepting, I'm waiting for a message coming from a request from a client, I will refer to that socket. So it's a file descriptor of the more abstract file descriptor. It's just general, okay? But now,
okay.
Now you cannot read from this. You must read from the file descriptor that is giving you back by accept, okay? There is one reason to do that. This is maybe a tricky reason, but it's a way of using the internal process structure. I will show you. So in that case, it is clear there is a serial server. Server opens the socket, binds listen, accept the communication, and this communication gives you a file descriptor in which to exchange data serially. You can just read, write. You may loop this, but in any case, you have to loop reading and writing with the client to which you are connected. Okay, and that's the way. But there is another way of working. If I succeed in opening the other file, I will show you. It was this one. Okay, very similar. Well, until where is my pen? Okay. Oh, what's happening? Oh, let me open again. No. What's happening? I can't write. Why? Pardon. Let me try again to. Okay, what? Oh, now it works. Sorry, but okay, I must. Now it should work, but the pen is not working anymore, so I must use the mouse of that terrible event. So you see here that the main is the same until here, listen, the same code. Socket, bind, listen. So you're listening in this file descriptor to this file descriptor. Then here I'm looping. This is a loop, which is strange loop. So the accept is inside the loop. In the previous example, you had directly the accept giving you the new socket file descriptor, the one that you needed to read and write. The same thing, but you loop here. You loop, so let me hide what is not interesting here. For example, okay. Let me hide here this. Hide, well, okay. So in that case, you accept the communication as in the previous case, but immediately after you fork. So from now on, from here on, the process that is running the server has a child. The child. And what's the code of the child? This is the code of the child. Which is the code of the father? So the original process is just this one.